This is my lab 4 presentation for Physics 2. The purpose of this lab was to analyze circuits and voltage behavior in basic and resistor capacitor circuits. Principles I used were energy conservation and current conservation. I was able to use the above principles to accurately predict time-dependent and steady-state current and voltage in circuits. The first principle I used is energy conservation, also known as the loop rule, which states that no energy can be created nor destroyed, meaning for a closed system, there should be no net change in energy or voltage. The closed system in this case is the circuit, so the net change in voltage must be zero. Current conservation states that the current in one part of a circuit will equal the current found in another part of the circuit for a series circuit, and for a parallel circuit, the sum of the currents in the nodes will equal the current of the overall circuit. For charge conservation and energy conservation in series circuits, the initial conditions were 0.02 amps and 3 volts. The current became negative if the ammeter was flipped, as measured by them, and the voltage was measured to be 3 volts when the voltmeter was added to the circuit because it effectively has infinite resistance, meaning that it takes up all of the voltage drops. The ammeter measured 0 amps when that happened because the voltmeter effectively created infinite resistance, meaning that there should be effectively 0 current. This is the potential versus position graph that I created from measuring the voltage drops across every segment of the previous circuit that I made. And the sum of all the voltage drops should equal 0, which they did, and the current should be 0.02 amps. I calculated the resistances to be 48 ohms for the 47 ohm resistor, 102 ohms for the 100 ohm resistor, 0 ohms for the wire, and 0 ohms for ammeter. For the RC circuit, the light shines brightly then dims over time to nothing when the capacitor is charged and discharged, and for charge plus discharge times, I got 7 seconds for 10 ohms of resistance and 13 seconds for 20 ohms of resistance. The system in the experiment was the circuit and its components, which are the batteries, wires, light bulb, and the capacitor, and the surroundings were the voltmeter, which had no effect on the system. The initial conditions were an EMF of 9 volts, the capacitor voltage at time equals 0 was 9 volts, light bulb / total circuit resistance of 30 ohms, and the capacitor had a 0.2 farad capacitance. The capacitor in the RC circuit was fully charged, 9 volts, then the battery was removed, and then the capacitor was connected to the light bulb in the circuit. The voltage across the capacitor was measured every 2 seconds for 20 seconds after the fully charged capacitor was connected, and I created a graph comparing the natural log of measured voltage divided by initial voltage to time to find the RC value using this equation down here. These are pictures of the experiment in progress. Charged capacitor, removed the battery, and then discharging capacitor. This is the chart that I made on the right of the equation that I previously showed versus time. And then the slope of the natural log of voltage over initial voltage versus time should be -1 over RC because of the equation below, and therefore RC should equal to -1 over slope, which is -1 over that number there. The comparison for the comparison between the prediction and the experiment, the RC value is predicted to be 6 in the circuit, and the RC value that was actually found from the slope was 6.006, which is incredibly close. Possible sources of error were the precision of data outputs like the ammeter and voltmeter, which would be random error, and then human error and timing measurements at the correct time intervals, which would be also random error. If I was doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter, this would likely create lower numbers for the measured current because a real ammeter will usually have some measurable effect on resistance because of its own finite resistance, unlike the ideal one, which had 0. If I was doing this lab in real life and used a real battery to charge a capacitor without a resistor in the circuit, the capacitor would likely charge extremely fast, but not infinitely so. And our ideal model would predict the capacitor to reach full charge instantaneously, but this wouldn't happen in real life because the batteries themselves have some internal resistance that would make the RC value non-zero, which means it takes some time for the resistor to fully charge. Thank you.